Good morning, students. We have earlier studied about the Fourier transformations and how to calculate the Fourier transformation and the inverse Fourier transformations of various functions. Today, we are going to discuss a very important property of the Fourier transformations, that is known as the convolution theorem for the Fourier transformations. Before going to that particular theorem, we have to define the convolution of two functions. What is the convolution of two functions? If fx and gx are two functions, defined on the interval minus infinite and infinite, then the convolution of these two functions fx and gx is denoted by f star z is equals to 1 upon root 2 pi integral minus infinite to infinite f of u z of x minus u du. This is the convolution of two functions f and z which are defined on the interval minus infinite to infinite. So this is the convolution of two functions. Now based on this definition of convolution of the function, we will define the convolution theorem for the Fourier transformation. So what is the convolution theorem for the Fourier transformations? First, the statement of the theorem is, there are two functions fx and gx. Let fx and gx and their first order derivatives are continuous on the closed interval minus infinite to infinite. Let the functions fx and gx and their first order derivative f dash x and g dash x are continuous on the interval minus infinite to infinite. Second, fx and gx are absolutely integral on this interval minus infinite and infinite. And third one is, if fp and gp are the Fourier transforms of the function fx and gx respectively, these three are the assumption, then the result says that the Fourier transformation of f star g, that is the Fourier transformation of the convolution of two functions f and g, Fourier transformation of f star g is equals to fp into gp. That is, the Fourier transformation of the convolution of two functions f and g is equals to the product of the Fourier transformations of the functions. Right, on the right hand side we see that fp into gp. fp is the Fourier transformation of fx and gp is the Fourier transformation of gx. So the Fourier transformation of the convolution of two functions f and g is equals to the product of the Fourier transformation of fx and gx, that is fp into gp. Or equivalently, we can say that f star g, by taking the inverse Laplace transformation, f star g, and f star g we have defined earlier, the convolution of two functions, f star g is equals to 1 upon root 2 pi integral minus infinite to infinite f of u z of x minus u du is equals to, if we take the inverse Laplace transformation, then the right hand side is the inverse Laplace transformation of fp into gp, that is equals to 1 upon root 2 pi integral minus infinite to infinite e raised to iota minus iota px fp gp into dp. Or equivalently, we can write this one as integral minus infinite to infinite f of u z of x minus u du is equals to integral minus infinite to infinite e raised to minus iota px f of p z of p dp. This is known as the convolution theorem for the Fourier transformation. So first we prove this theorem. What is the proof of this theorem? The proof of this theorem, convolution theorem. Here fp and gp are the Fourier transformation of the function fx. So first we write the Fourier transformation. Here fp is the Fourier transformation of the function fx. So this is equals to 1 upon root 2 pi integral minus infinite to infinite e raised to iota px fx dx, number 1, and gp is equals to 1 upon root 2 pi integral minus infinite to infinite e raised to iota px gx dx, number 2. These are the Fourier transformation of the function fx and gx. Now, by definition, The left hand side is the Fourier transformation of f star g with respect to p. By definition, we have to find the Fourier transformation of f star g. Now, what is the Fourier transformation of f star g? And f star g is the convolution of two functions. So we write the convolution of two functions as 1 upon root 2 pi integral minus infinite to infinite f of u g of x minus u du. This is the convolution, and we have to take the Fourier transformation of this function with respect to the parameter p. Now we write the definition of the Fourier transformation. The Fourier transformation of a function is integral e raised to iota px type. So we can write the Fourier transformation of this function as 1 upon root 2 pi integral minus infinite to infinite e raised to iota px, and the function is 1 upon root 2 pi integral minus infinite to infinite f of u g of x minus u du, and then integrate with respect to x. Or we can write it as 1 upon 2 pi integral minus infinite to infinite e raised to iota px integral minus infinite to infinite f of u g of x minus u du dx. Here we have to integrate first with respect to u and then with respect to x. Now if we change the order of integration, changing the order of integration, changing the order of integration. Here first we have to we integrate with respect to u and then with respect to x. Now we change the order of integration. First we integrate with respect to x, then with respect to u. We get this is equals to 1 upon 2 pi integral minus infinite to infinite. First we integrate with respect to u, with respect to x and then u. So we get it is f of u integral minus infinite to infinite e raised to iota px into z of x minus u dx, and then integrate it with respect to u. We can write it as 1 upon root 2 pi integral minus infinite to infinite f of u into 1 upon root 2 pi integral minus infinite to infinite e raised to iota px g of x minus u dx d. Now if we substitute x minus u, put x minus u is equals to t, then x is equals to u plus t. So this is equals to 1 upon root 2 pi integral minus infinite to infinite f of u. This is into 1 upon root 2 pi integral minus infinite to infinite e raised to iota p x, that is u plus t, z of t x is u plus t, z of t dt, and then we integrate with respect to u. This can be written as 1 upon root 2 pi integral minus infinite to infinite f of u. If we take e raised to iota p outside the first interior integral, then this is e raised to iota pu, and 1 upon root 2 pi integral minus infinite to infinite e raised to iota pt zt dt, and then with respect to u. The inner integral we see by the equation number 2nd. This is the Fourier transformation of the function gx or gt, and that is gp. So this is equals to 1 upon root 2 pi integral minus infinite to infinite e raised to iota pu f of u GP du. GP, if we take GP outside the integral, then we get GP into 1 upon root 2 pi integral minus infinite to infinite e raised to iota pu f of pu du. And we know that the value in the integral is the Fourier transformation of the function fx, and which is fp. So this is equals to fp into gp. So we get the Fourier transformation of f star z with respect to p is equals to fp into gp. By taking the inverse Laplace transformation, we see here this is equals to f star z. F star z is the convolution of the two functions. We write it as 1 upon root 2 pi integral minus infinite to infinite f of u z of x minus u du. This is equals to the inverse Fourier transformation of f of p z of p with respect to x. Or we write the inverse Fourier transformation, we get 1 upon root 2 pi integral minus infinite to infinite f of u z of x minus u du is equals to 1 upon root 2 pi integral minus infinite to infinite e raised to minus iota px fp into zp into dp, or this is equals to integral minus infinite to infinite f of u z of x minus u du is equals to integral minus infinite to infinite e raised to minus iota px f of p z of p dp, which is the required convolution theorem for the Fourier transformation. So, by the using of the definition of the Fourier transformation and the convolution of the two functions, we can prove the Fourier convolution theorem for the Fourier transformation, which shows that the Fourier transformation of the two functions, Fourier transformation of the convolution of two functions f and g is equals to the product of the Fourier transformation of those functions. Thank you very much.